All right, so we are starting chapter 8 today. We're going to work on section 8.1. We're going to talk about distributions of the sample mean with the normal population and with a non-normal population and what those look like and what we can do with those. So let me shut that ringer off that just went on and we will get going. Okay, so the sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample size of n. So these, don't worry about memorizing these. This is just basically what they are. You'll get the gist of it as we go. Vocabulary is just kind of that. I give it to you and it's like, what does that mean? And then it kind of makes sense as we go. So the sampling distribution of a sample mean. So x bar is the probability distribution of all possible values of the random variable x bar computed from a sample size of n from a population with mean mu and standard deviation sigma. Just a second, and I'm going to explain that to you. So here's an example. The government wants to determine the mean income of all U.S. households. They're not going to survey every household. That would be really difficult, time-consuming, expensive. So what they do instead is they do random sampling. So they, in 2013, there was a population survey of about 250,000 randomly selected households. They used those to determine that the mean household income was 72,641. If they took a second random sample of the same size and got that mean as 71,849, and then they take a third random sample and find that mean 72,978. All of those means are different, and they could base the population mean. They can, whichever one serves their purpose better, they can grab those. Or instead, what they could do is they can take those three sample means and they can take the mean of those means and they're going to get a more accurate representation of what the average income is. So they would take that 72,641, 71,849, and 72,978. Then they would take the average of those. They would get the mean of those, and then that mean of means would be more accurate. So we still will call it a sample, so we're still going to be x bar. We're not going to call it mu. It's still x bar because it is still a sample, because the households selected will vary. So the sample mean varies, and we're just going to call it an x bar because it's a sample. Okay, so hopefully as we go, this will make more sense. So here's what sampling distributions look like. So first you take a simple random sample of size n, so whatever number that is, compute the mean of that. Then assuming we're sampling from a finite population, do it again. Take another sample size n and find the mean of that. And then take another random sample size n, take another one, and keep going and going. And it is quite possible you could end up with the same person in two different samples, but it wouldn't be all the same people. You can't have the exact same sample twice. So just keep taking your random samples and find the means of those samples, and then take all of those means and find the mean of those means. All right. So here's an example here. So the weights of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02 grams. We're going to approximate the sampling distribution of the sample mean by obtaining 200 simple random samples of n equals 5 from this population. So basically what happened was they grabbed 5 pennies and then they averaged their weights. Grab 5 more pennies, average their weights. They do that 200 times. They grabbed 5 pennies and averaged their weights 200 times. So the data on the following slide is going to be those 200 simple random samples of size 5. So there would be the means of all of those 200 samples that we grabbed 5 pennies. So this right here, this would be 5 pennies that we grabbed, and here we took the mean of those, and here we took the mean of 200 different samples of 5. So notice how all these means are fairly close. It's because it's the means, it's not the actual weights. Going back here, there's a little bit bigger difference between the weights. These are all really close. So the mean of 200 sample means is 2.46. That is the same as the mean of the population. The standard deviation of the sample mean is 0.0086. That's smaller than the standard deviation of the whole population because we are dealing with means. I'm going to show you the histogram of those sample means. This is a pretty nice bell shape. Right here, this one right here is a little bit taller, but it is a pretty decent bell shape. Okay, but what role does n play in the sample size? Or what role does the sample size play in the standard deviation of the distribution of the sample mean? So as the sample size increases, the standard deviation of the distribution of the sample mean is going to decrease. So the mean of the means, the standard deviation of the means is going to decrease. We're going to get closer and closer and closer. Remember that law of large numbers? So as we have larger sample sizes, we're going to get closer and closer and closer to that population mean. And that means that the spread of our data is going to be less, because remember, standard deviation is the spread of the data. Because we are looking at means, the larger our sample size, the closer our mean is going to be to the population mean. Therefore, our standard deviation is going to get smaller because we are not going to be so spread out. So suppose that instead of our sample size being 5, our sample size was 20 from the population of the weights of pennies. So instead of sample size so this is my population standard deviation here, my population mean right there. So we're going to use n equals 20 instead of n equals 5. See what happens there. So this is a much prettier bell curve when n equals 20. It's much nicer, much cleaner and more bell-shaped. And our standard deviation is now 0.0045. So as expected, our standard deviation is getting smaller. So obviously, the larger sample sizes within our trials is better. So as n gets larger, we're going to get closer and closer and closer to that sample or that population mean. All right. Okay, so things got wonky here. I'm not sure what's going on here. Okay, I'm not sure why it's not looking okay on here, so I'm going to have to help. So suppose that the simple random sample of size n is drawn from a large population with mean mu and standard deviation of sigma. The sample distribution of x, this should be mean sub x, so we'll have mean mu sub x and a standard deviation. I'm not sure what happened here because it looks fine on my other screen. So the way that we calculate standard deviation, I'm really sorry this didn't show up well. I'm hoping it shows up good on the one that you download. So our sample mean, our mean of our means, mu sub x bar, is always going to be the same. It's always going to be the same as our population mean. So population mean equals mu sub x bar. The sample mean, the mean of the means is going to be the same. So when it asks you mu sub x bar, it's always going to be the same as the population mean you are given. So the standard deviation is also called the standard error. You may be asked for standard error. You may be asked for the new standard deviation. We're going to use, so sigma sub x bar equals the standard deviation, the population standard deviation divided by square root of n. So the population standard deviation divided by the square root of our sample size. So let's do some problems. This might help. Okay, this is sigma sub x bar. So the standard error is sigma sub x bar. Let's move on. See, this one turned out just fine. So for the population presented earlier, if we draw a single random sample, the sampling distribution x bar will have a mean mu sub x bar is the same as the population, so it's 2.46. Standard deviation, we do sigma divided by the square root of n, so 0.02, that was our population standard deviation, divided by the square root of 5, and this is the standard deviation you are going to use in your calculations. You will use the 0.0089 in your calculations in this unit or this section. So the standard error or mean is close to the approximate standard error of 0.0086 found in our earlier example. So calculating this way is really close to what we got by putting it all into our calculator and calculating the standard deviation. So we are going to use this number right here. So when we have a sample size of 10, once again, I put the standard deviation from the population divided by the square root of 20, and I get 0.0045. It's exactly the same as our approximate standard error of our earlier example. So remember, this is how you're going to calculate standard deviation, which is also standard error in the homework. If it asks you what the standard deviation is, or the standard error, or sigma sub x bar, this is the formula you will use. So if a random variable x is normally distributed, the distribution of the sample mean x bar is also normally distributed. So if our population is normally distributed, our distribution of the sample means will also be normally distributed. So here's another example. So an intelligence quotient, or IQ, is a measurement of intelligence derived from a standardized test. Scores on this test are approximately normally distributed with a mean score of 100 and a standard deviation of 15. So our population mean is 100, standard deviation is 15. We're going to find mu sub x and standard deviation, or sigma sub x, with a population of a sample size n equals 9. So just find those two things. Find the mu sub x bar and the sigma sub x bar using what we just did with the last problem. So go ahead and pause. Our sample size is 9. All right, so let's take a look at this. So our mu sub x bar, remember that is the same thing as the population mean. Our standard deviation sub x bar is our standard deviation here, so it's 15 divided by the square root of 9. So 15 divided by 3, so it's going to be 5. So this right here is my standard deviation, or standard error, same thing. And this right here is my mu sub x bar. All right. So going back to the weight of pennies, the weight of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02 grams. We want to know that the probability that in a simple random sample of 10 pennies minted after 1982 we obtain a sample mean of at least 2.465 grams. So we want to know what the probability is that if we took 10 pennies out, that their mean would be approximately, or would be at least 2.465 grams. So let's take a look. So at least means greater than. So we are normally distributed. Once again, I don't have all my lovely symbols there. I don't know why it's doing this to me. It is not very kind. So we're going to take a look. So we have our mu sub x bar is 2.46, because remember, it is the same thing as the population mean. The sigma sub x bar, so we have our 0.02, that is the standard deviation, the population, divided by the square root of 10. That gives me 0.0063. So we're going to calculate the z-score here. Remember, in order to calculate a z-score, we do, our given point, so what we're looking for, minus the mean. So the data point that we were looking at, remember, was 2.465. So 2.465 minus the mean divided by the standard deviation. As I said before, this is the standard deviation you are going to use. You kind of ignore the population standard deviation after you've calculated your new one. So divided by that new one, my z-score is 0.79. So I'm looking for the probability that z is greater than 0.79. So I want to know the probability that we are up here. Remember our z table, our table 5? It gives me, table 5 will give me this piece down here. It'll give me everything to the left of that, and I want everything to the right of that. So what I'm going to do first here is I'm going to look for z-score 0.79. So here's 7. I'm going to do some highlighting. Here's 0.7. We go to the hundredths place down here, 0.79. So that's going to be, whoa. So that's going to be 1 minus, because we're looking for greater than, and this right here gives me less than. I have to do 1 minus 0.7852. So that gives me 1 minus 0.7852, and that's going to give me 0.2148. So the probability that the sample mean of those 10 pennies that I draw is less than, or sorry, greater than 2.465 is 2.2148. I'm guessing you're probably going to want to use your calculator instead of the z-table, though I'm really partial to these z-tables. So let's take a look at that. So if I put it in my calculator, I can do normal CDF. So remember, we do lower bound, upper bound. That's really ugly. Upper bound, comma, mean, mu sub x bar, comma, sigma sub x bar. This is what we're looking for, the lower bound, comma, upper bound, mu sub x bar, sigma sub x bar. Put that into your calculator and you should get the same thing. Let me see what happens. I didn't actually check this because I didn't check it. 6.5, comma. Okay, whoops. I didn't put, yep, I ended up with 0.2137. Did I put it all in correctly? Looks like I put it in correctly. It's really close, and a lot of that is because on the z table it's kind of an estimate, and so 2.137, it's close enough. But especially if we're it would probably tell you to round to 2 decimal places, so it'd end up with 0.21. Both of them are 0.21, so the difference is negligible. Okay, let's move on. I would like you to try this one using exactly the method that I just did on the other one. You can either use z-scores with the z-table, or you could just use your calculator. So the IQX of humans is approximately normally distributed with a mean mu equals 100 and standard deviation sigma equals 15. Compute the probability that a simple random sample of size n equals 10 results in a sample mean greater than 110. That is, compute probability that x bar is greater than 110. So go ahead and pause this, try to do this problem on your own, and we will come back and we'll do it together in just a moment. All right, hopefully you got that done. So let's take a look. First thing I'm going to do is write down that my mu sub x bar is 100. My standard deviation, my sigma sub x bar, is going to be 15 divided by square root of 10. So 15 divided by the square root of 10 is approximately 4.74. So this right here is the standard deviation that I will be using for my calculations. So if I want to calculate my z-score, I have the z-score equals 110 minus 100 over 4.74. So I get a z-score of about 2.1097. I'm going to take a look on my chart here. 2.11 is right there. Because we are looking for greater than, so the z table gives me less than. I need to do 1 minus 0.9826. So my probability that x bar is greater than 110 is approximately 0.0174. Now you can go ahead and put that in your calculator. If you put that into your calculator, you would do normal CDF. Your lower bound would be 110. Upper bound would be infinity. Mu is 100. Standard deviation is 4.74. I don't think I put this in my calculator, so I'm going to put that in my calculator right now. We will see how close I get to what I got using the z-table. And I got 0.0174. I got the same thing. Beautiful. I love when that happens. If you have any questions on that, if you didn't get the right answer and you're confused, go ahead and send me a message or an email, and I'll be happy to help you because that's what I do. All right. So we're going to take a look now at when the population is not normal. Because I said, if the population is normal, then your means of means will all end up being normal. So this table right here shows a population that is not normal. This is a uniform distribution. We talked about this in the last chapter. Uniform distribution because the probability of each thing happening is is the same, and so my relative frequency of each of them. This is not going to be a normal population. However, as I start taking the means of means, so here I'm going to do 200 simple random samples. The size is 4, and I'm going to calculate the sample mean for each of the 200 samples and then get the means of all of that, and then I'm going to repeat for 10 and 20. Let me show you what happens to these distributions as we start finding our means of means. So here's 200 sample means with each sample is 4. This is pretty normal distribution. This is not too bad. Let's get a little bit higher. Let's see when n is 10. That is an even better distribution. Now take a look here. This is a perfect bell curve. This could not be more beautiful. So when n equals 30, so when each of my samples, I do 30 rolls, take the mean of those. 30 rolls, take the mean of those. 30 rolls, take the mean of those. We do that 200 times, and then we put them on our frequency table. So as you can see that my means end up with a nice bell curve. This is a really great way to get a normal distribution out of something that is not normally distributed. Okay, so here's some key points from, here. There we go. Okay. Okay, the mean of the sampling distribution is equal to the mean of the parent population. So the mean is equal to the mean of the parent population. Standard deviation, we use this right here, is sigma divided by the square root of n, no matter what our population size or sample size is. The shape of the distribution will become approximately normal shaped as the size of n increases, regardless of the shape of the population. This is important. This central limit theorem tells us as the size of n increases, no matter what our population shape is, we will get a normal distribution. This distribution of the sample means will become normal. Okay, we have one more problem, and I want you to try this one on your own from the beginning. So Suppose that the mean time for an oil change at a 10-minute oil change is 11.4 minutes with a standard deviation of 3.2 minutes. If a random sample of n equals 35 oil changes is selected, describe the sampling distribution of the mean. So what this means, describe the sampling distribution of the mean, that means give me the mu sub x bar, so give me the mu sub x bar and give me your new standard deviation or your standard error. Give me both of those things for that one. For this one right here, I want you to calculate the probability that the mean oil change time is less than 11 minutes. So go ahead and pause this, complete this problem, and come back and we will do it together. All right, so I'm hoping you did that, hoping you paused this. So describing the sampling distribution, we have mean sub x bar is going to be this mean right here. It's going to be 11.4 minutes. Sigma sub x bar is going to be 3.2, our standard deviation, divided by the square root of 35, because that's our n. So that gives us about 0.5404. So this right here is the standard deviation that we are going to use when we use our normal CDF. So what you put in your calculator, normal CDF, we're looking for less than 11 minutes, so it'd be negative E99. Upper bound is 11. Our mean is 11.4, and our standard deviation is 0.5404. And once you put that in your calculator, you should have gotten 0.2298. So really close to 23% probability that the mean time will be less than 11 minutes. It's not very good. That is not a very good probability. I'm thinking that they need to change their 10-minute oil change name to 11.5-minute oil change or 12-minute oil change, because clearly it's not going to be below 11 minutes. All right, so your homework on this section is due next week on, it's due next week on Tuesday, isn't it? Yep, due next week on Tuesday. We will also have quiz 5 that's also due next week on Tuesday, because I believe next week, Monday, is Memorial Day. So even though, unfortunately, Boatnik is canceled, is it Memorial Day? I believe, yes. Okay, Boatnik is canceled this year. However, Memorial Day is still a thing. It is still a holiday. We were told not to have anything due on that holiday, and I may or may not be online. I probably will, because I'm me. Anyway, have any questions, send me an email, send me a message. Thank you.